I hope you're on page 16. Let's take a look at section 3.5. This is the inverse function. All right. So you have some sense of understanding what an inverse function is. We'll look at it today, and then we'll look at the inverse function once again on Wednesday when I'm back. Okay. And then, yes, all of this is included on the test that is next Friday. Right. So keep in mind, next Thursday is a review day. However, there's a lot of review materials posted. So over the weekend and on your PA day, you can work on preparing yourself for the test. Right. There's one lesson that you would not have been taught yet. Okay. So let's look at the learning goals for this lesson. And the reason why I show this is so you have an sort of a goal of what you want to be able to understand by the end of either the lesson or of doing the homework and reviewing the lesson. Okay, so the first thing is to understand that inverting the function undoes the operations of the function, of the original function. Okay, so the inverse is like undoing a function. Next, understand that the notation f of f to the power of -1 means means the inverse of the function, and sometimes we'll say f inverse or the inverse of the function, just so you know sort of how to communicate about this. Also, you are going to learn how to invert a function by switching the ordered pairs, like the pairs of a point. And you're going to recognize, hopefully, that the inverse of a function is actually a reflection, right? We know vertical and horizontal reflection in the line y equals x. Now, aside from the slideshow, you've actually been exposed to inverse functions already. And there's one in particular that you've actually called it inverse. So when you take, let's say, the sine of 0, okay, and now I have to say, I forget, I think sine of 0 is 0. Let me quickly check. Anyone else remember? Let's say 0 sine. Okay, that's correct. So that means yes. All right. Actually, let's try something different. Let's do, when I take the sine of 90 degrees, my output, so my input is the 90, right? My output is 1. Okay, that's the ratio I get. Now, what if instead we are given the ratio, not the angle, and we want to find the angle? Do you remember how we did that? Well, we would find the angle by using the sine inverse function or the sine inverse button, where you'd have to press shift on your calculator, right? And this would give you the output of an angle. And so sine and sine inverse are are opposite functions, and they're inverses of each other. Okay, so you have some experience of this. You may not have realized that you were doing what an inverse was. Now, let's look back at the function machine. Okay, so originally what we learned with a function machine is that we take an input. Let's call the input x. Okay, we're always going to call the input x. We put an x into a function. The function does something, and then what it spits out is the f of x. And we've in the past said, oh, f of x, sometimes we call that the y. Okay, so whatever we get as our output is the function of x. Okay, now let's take the function machine that is used for the inverse function, right? It's the backwards function. So now our input goes into the output spout, right? So we still call it an x, which is a bit confusing, but we still call it an x, right? You'd want to call it a y. And if it helps, just think of it as putting the y in here. Okay, but whatever was spit out of this function goes here. I'll use a different color. Whatever was spit out of this original function machine gets placed back in the inverse function machine. It goes backwards, does all the opposite operations, and what gets spit out? Well, the f inverse of that function. Okay, and if we wanted, we could show that this is an endless loop, that you could take the output of the inverse function, put it back in the original function, and what would come out would be f of x. Okay, a bit confusing. Let's try an example. Let's look at the function f of x equals 2x plus 1. Okay, so a nice linear function. And we're going to find the inverse function by undoing the operations. So in order to do this, we need to understand the operations of the original function and the order of the operations. Okay, so what's our input? Well, the input is going to be the x. Okay, so we take an x, we place it into this equation or function, right? And what is the first thing that is done to the x in this function? Well, it's multiplied by 2, right? 2 times x. And what comes out of that? Well, it would be 2x. Okay, well, and then what happens after that, after we do 2x, now that we've taken care of the 2x, is that now we will add 1. And what is spit out of the function machine after that step is 2x plus 1. Okay, so this is our output. And this output actually equals to some number. Okay, usually we call it a y. Now, I know it's confusing, but there's a reason why I still want to call the input of the inverse function an x. Now, so let's say I get a number like 5 as my output. I'm going to take that 5 and put it into the inverse function to get the original value that was plugged in. For the sake of this example, I'm going to call the input of the inverse function x once again. But now what we're doing is we're actually going backwards through the original function. So what was done last to this function? Well, we added 1. Okay, so we are going to do that first. And not only that, we're actually going to do it oppositely. So instead of adding 1, we're going to subtract 1. So when you take x and subtract 1, that gives us x minus 1. Okay, what's the next thing that's going to happen? So let's keep going backwards in our function machine. We've taken care of the plus 1, and now we have to do the opposite of times 2. So the next inverse operation will be divided by 2. And so that means that we take our x minus 1 and we divide the entire binomial by 2. And so this is the output of the inverse function. Okay, and so what we want to see, what we're looking at is this. F of x, the function of x, I'll make it orange, is 2x plus 1. And the inverse function of x is x minus 1 divided by 2. Now, in each of these cases, the x's are actually going to be different. Like, look at these tables of values. For the function, my x's are 0, 1, 2, 3. Whereas for the f inverse, my x's are 1, 3, 5, 7. So x just represents an input. We're always going to use x as an input. Okay, but remember, x can be any number, and it could be a variety of numbers. So if my input is 0, I plug it into the equation. 2 times 0 plus 1, well, that's 1. If my input is 1, 2 times 1 plus 1, oh, that's 3. right? And so I end up with a table of values, and then 2 times 2 plus 1, that's 5. 3 times 2 plus 1 is 7. So I get this table of values here for the original function, right? And I can graph it, and it's a straight line with a slope of 2 and a y-intercept of 1, right? Okay. Well, what if I take the output and make it the input? Okay, so I'm taking the 3 and I'm making that the input, taking the 1, making that the input, because I want to prove that this function truly is an inverse function. Because if it's an inverse, if I put the output into the equation, I should get the original input. So when the output was 1, okay, let's see. 1 minus 1, all divided by 2. There you go. It is 0. And what was the original input? It was 0. Well, let's see. Okay, I'm going to test the output of 7. I'm going to test the original output of 7. So if I put it into the inverse function, I get 7 minus 1, that's 6. 6 divided by 2 is 3. See? The output of the inverse function is the original input. Let's say that. Output of original function is the input of the inverse function. Okay. And in other words, again, we can see that the output of f of x is now the input of f prime x, or f inverse x. All right. Sorry, not f prime, f inverse. All right. And so what do you notice about these points and these points, these points and these points? And if I put in yet another coordinate, if I said 4 and 9, what would my input and output be? Well, we know it would be 9 and 4. And so, therefore, if one point on the graph or on the function of 2x of the original function is 3, 7, and the point that is on the inverse function is 7, 3. Right? So I'm just taking the inputs and the outputs. And I see, oh, all that's changing is that they swap places. Well, in that case, I can say that if I have an x and y for the original function, then the coordinates of the inverse function will be y and x. Right? This is the inverse. So all I have to do is swap the two coordinate points. Okay, take a second to digest that. Okay, and let's try an example. Find the coordinates of the inverse of this relation. So again, a relation or a function, doesn't matter. Well, actually, in this case, this is a function. A relation is just a collection of points. Right here we have 3 points. Is it a discrete function or a continuous function? It's discrete. Great. Well, let's find the coordinates of the inverse of this function. So all we do is we take these points and we swap the x's and y's. So when I have -3, 4, I swap it, and now the x becomes 4, the y becomes -3. For the second point, the 0 and 7 swap, and we have 7, 0. And for the last point, the 2 and 9 swap, we have 9 and 2. That's it. So I can very easily find the inverse coordinates, or the coordinates of an inverse function. Okay, let's look at example 2a. Given the function f of x is 3x minus 2, find the inverse of the function. Now, oh, look here. Do you remember this? Nota bene. Nota bene, from Latin, a good note or an important note. Use the concept of reversing or undoing the operations originally performed on X, and a flowchart may be helpful. So I will make one more flowchart before I teach you a quicker strategy. All right, so let's take the original function. Okay, so for f of x, we have that the input is x. Okay, what's the first operation done to the x? You got it, times 3. Okay, what do I get when I multiply x by 3? Well, I get 3x. Okay, what's the second operation? Say it out loud. You got it. I hope you're saying it out loud. Participate, folks. It's better for your brain. I feel like Liam in the back is talking to me, right, Liam? Yeah, yeah. And Marley's like, shh, you're embarrassing me. No, no, no. This is exactly what I want. All right. So, and then when I subtract 2, I get 3x minus 2. All right. So that's the output. Now let's look at the f inverse. Again, the input is an x, but it doesn't mean that these two x are the same number. Not same number. It just means that's what you're throwing into the function machine. All right, so if I put a value, which we represent as x, into the inverse function, means I have to reverse this function. So what will be the first step? Well, I will first reverse the negative 2 by adding 2. So I get x plus 2. Great. After that, I will reverse the next operation, which was the times 3, and I will reverse it by dividing by 3. And that gives me x plus 2, and now the entire binomial has to be divided by 3. Right? So this is what we've seen before, how to find the inverse function. And you say, I hear you. You're like, Ms. Sly, there's got to be a faster way. This is so annoying. I don't want to draw flowcharts for the entire unit. And I agree. Neither do I. Now that we understand how, now that we understand these flowcharts, let me show you a quicker way. So back in example 1, we took the x and the y and we swapped their places. And that's what we're going to do within the function. So the first step, we're going to let y equals f of x. So if I start with, so I'm using the original function from 2a, f of x equals 3x minus 2. Now in step 1, I'm being told to write y instead of f of x. So y equals 3x minus 2. Okay, and here's the big one. Here's the big one. I'm going to circle it. It's so cool. Yeah, 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 yeah. Switching x and y values. So, where you have an x and y, they swap places. Watch this. So instead of the y, so this is step 2, I'm writing x. And instead of the x, I'm writing y. The equation did not change. Okay, I just swapped the x and y. Why did I do this? Well, I did it for step 3. Now I'm going to isolate for y. Okay, so if I start with x equals 3y minus 2, as I isolate for y, I bring the negative 2 over, so I get x plus 2. Oh, that looks like an opposite equation, or an opposite operation. And then, what is the opposite of 3 times? Well, then I divide by 3, and I'm left with y being x plus 2 over 3. Where have we seen that before? Oh, we've seen that there. And now, as our last step, we must state that we have found the inverse. So we swap the y and the f inverse again. So instead of writing y, we write f inverse of x equals x plus 2 over 3. Okay, so you might like this. And I do find that as the functions become more complex, it's much easier, more straightforward to just swap the variables. Okay, let's do one more example. And so what you're going to do, you will try this in the homework. Okay, when you need to find the inverse of functions, you can try it using the flowchart, and you can try it by swapping the variables. Okay, lastly, let's find the inverse using a graph. So starting with the parent function or the original function of x squared, so we have a parabola. So we know that the vertex of a parent parabola is at 1, and we know that the step pattern for a parent parabola is 1, 3, 5, 7. So 1 across, 1 up, 1 across, 3 up, 1 across, 5 up. That gets me to, I did something wrong. Yes. Okay, 3 up goes to 4, 5 up goes to 9. And then this is a symmetrical function. And so as a result, I just make sure that the lines are, the points are symmetrical. And now nice and carefully, I draw the actual parabola. Some of you on your quiz forgot to graph arrows. So you actually, yeah, you do lose marks because by drawing those arrows, you are showing your understanding that this function continues on forever and ever. And actually, I want to show you another mistake that students made. Man, this is so hard to write it on a tablet. It's to graph the parabola like that. Do you see what my mistake is? Well, this function does not pass the vertical line test, right? Nope, it fails. Parabolas do not go inward. Radical functions do not go like this. Reciprocal functions do not go like this, right? So be accurate as you're, even if you're sketching, be accurate, because I will remove marks if you're saying, I'm not fully understanding that a function can't fold onto itself. Okay. And now let's label this function. F of x equals x squared, right? I want you to label functions. And if you are to label a point, it is not on the side of the paper. It is right next to that point. So this point is 3, 9. Okay. Determine, and now let's graph the F inverse. And so the easiest way to do that is to take the coordinates of these points and swap them. So if I swap 3 and 9, I get 9, 3. So that means x is 9, y is 3. Right? That's 9, 3. Let's find another point. This point is 2, 4. So the inverse of that is 4, 2. Oops, that's supposed to be green. Okay, go ahead and graph the inverse of this quadratic function by swapping the points. Ooh, look at this. 1, 1 is an invariant point. Let's write that down. Invariant point, because it isn't affected. It does not move, right? As is 0, 0. Starting to look like a radical function, wouldn't you say? But let's not forget that we have these points here, right, in the third quadrant. So I've got, this is negative 1, 1, which when swapped is 1, negative 1, right? 1, negative 1. I've got negative 2, 4, which when swapped is 4, negative 2. And then 9, negative 3. Whoa. All right, what are our concerns? Mustafa, you're looking at this and you're like, nah, not liking it. Not liking it at all, right? So we're calling this the F inverse of X. Okay. What do we not like about it? Yeah, that's right, Mustafa. Actually, oh no, it was Zach that told him. Okay. Yeah. This does not pass the vertical line test. So it's not a function. And the truth is, it's not. It's an inverse function. Okay. Now, I want you to take your piece of paper and you can tell that these two parabolas are the same shape, right? What I want you to do, and I really want you to do it, I want you to take this paper and fold the parabolas on top of each other so that they're touching each other. Okay, so you know the shape is the same. And I want you to actually fold your paper, fold it so that the green parabola goes on top of your pink parabola, and then make a crease. Make a crease on your paper so that you can see where on the graph that crease is. Okay, take a pause to do that. Okay, and so what you have found is that the the line upon which the parabola folds is this line. So we are talking about a reflection, folks. It's just that we're not talking about a vertical reflection nor a horizontal reflection. What would you call this? Yeah, it's like a diagonal reflection. What? Like a diagonal reflection on a Friday, Miss Sly? You gotta be kidding me. That's right. Yes, but we don't actually call it a diagonal reflection. What we call this is we look at what is the equation of this axis. Okay, this is an axis of reflection. And what is the equation? Well, I see it's a linear function. I see the y-intercept is 0. And what is the slope of this function? 1 across, 1 up, 1 across, 1 up, 1 across, 1 up. That's right. The slope is 1. And so this blue dotted line here is actually the linear function of y equals x. It's the parent linear function. And so what we can say is that f of x equals, f of x is, wait, I need the proper phrasing. One second, give me a second. Okay. Okay, so what I can say is that the inverse of f of x, okay, so the inverse of the original function is a reflection on y equals x. Okay, so we're actually stating the equation or the linear equation upon which the function is reflected. And this is true for all inverse functions, right? So if I were to draw a heart, okay, and I think you do this in your practice, and I folded it on this dotted line, my inverse function would be this heart, okay, because I folded it on top of itself over that crease. Pretty cool, eh? I know. All right, folks, I know you miss me, but I know you are in wonderful hands with Miss Copland. Keep in mind that you have the quiz makeup that's coming up on Tuesday. Now, I have changed my mind. It's going to be even better. So what I've decided is that the mark you get on that quiz will replace the mark you got on the original test for application. So if you did not do great on the word problems, you got like whatever, like 2 out of 6, and you do better with my quiz, you get 4.5 out of 6. I will replace that mark, not just add it as an additional mark. I will fully replace it. Okay, so that is definite motivation to study for that makeup quiz that we're going to have on Tuesday. All right, and I will still post a little blurb just to give you the topics that will be on that quiz. Folks, have a wonderful weekend. Definitely take some time for math every day if you can, because this course is demanding. Because this test obviously will be challenging, not too challenging, but you need to take time to prepare yourself. Have a wonderful weekend. Bye, guys.